Okay, so here we are. We're talking about wave properties now. This is topic 4, section 5. So far, with waves, all we've been discussing are one-dimensional waves, like waves on a string or waves on a bouncy spring. But now we're going to start to see two-dimensional waves. Whereas we modeled 1D waves with strings and springs, two-dimensional waves we model using water waves. So we look at these waves in the water from above, and we examine the crests that are sent out in two dimensions, to the north, the south, the east, and the west, when viewed from above. If you drop a ball into a completely flat lake, what happens? You send ripples out from the point of impact. So in your notes, I want you to draw 4 concentric circles, and these will represent the four particular ripples that have had time to spread out. We are going to label these, and first I'm going to show you the 4 circles you should have, and then we're going to look at some definitions, and then we'll add in labels after the definitions have been explained. So here is the source, right? This is where that rock, here's where that ball, rather, hits the lake. Right? So it hits the lake and then it bounces up and down. And these ripples are sent out like that. So draw those 4 ripples, those 4 circles, into your notes in the space provided. A wavefront is a line that we draw which adjoins or joins adjacent crests. Rays are lines that we draw to show the direction of the waves. And they're always drawn at right angles to the wavefronts. Each individual wave will always pass through multiple wavefronts, which is to say it passes through multiple crests, because wavefronts are the crests. So that means that every single ray we might draw into a wave diagram like this, every ray represents a complete displacement position sine curve, right, where the wavefronts are the crests. Circular wavefronts are produced by a point disturbance, like a ball thrown into a single point in a flat lake. And their rays are radial, which means that the rays move out from that point, from the source, out along radii of the circle. So here's our point, right? This is where the ball lands. And then these ripples are sent out. But the ripples, the circles I've drawn, those aren't just ripples. We're going to see what those are. First, let's label the source. That's where the ball hits the lake. Now, these ripples really represent wavefronts. These are the crests. That's where the ripples are at a peak. Between every 2 wavefronts, there's a minimum, a trough. And remember, I've just taken a snapshot in time, which has showed, which is showing and has shown these 4 ripples. But if I let more time pass, more ripples might be produced. So here's the first wavefront. Here's another wavefront. Each of these circles is a wavefront. And then we could draw rays, and the rays show the direction that these waves, or the wavefronts, are traveling in. So the waves are traveling from the source outward, like this. And look at that, those are radii. Each one is a radius. And so we say that these lines are radial. That's a ray, and these other 2 are also rays. Now, here's something we're going to add in. These distances here, which I'm showing with the arrows, notice that they are all the same, and that's intentional. If you actually took a photo of a ball and took a photo a few seconds after the waves had been traveling out, the ripples, you would notice that the distances between 2 crests is the same. Well, wait a second. I just said that this is the wavelength. It's the distance between 2 crests, adjacent crests. Because remember, the wavefront represents the crests. So that distance, if you were to get a ruler and measure it, that tells you the wavelength, because it's the distance between 2 crests. So make sure all of these things are in your picture. Before flipping on to the next page, right, I want you to write plain wavefronts in the space at the very bottom of this page. So we're on the same page where this drawing is shown. And we're right below the circular wavefronts are produced, that bullet. So plane wavefronts, here we go. Now I want you to draw something different. It's going to be a diagram like this, but instead of having a circular wavefront, we're going to see wavefronts that are straight lines and that are all parallel to each other. So here is our source. Imagine that you take a really long, let's say this is a meter stick. You take a meter stick and you just drop it straight down into a lake, a perfectly still lake. Right? Ripples will be sent out like this. And of course ripples will be sent on the other side, but we're ignoring the other side right now. Each of these is a wavefront, each of those ripples. So that means each of these drawings, each of these lines, shows where the crests are located. And I take a snapshot, and I take this snapshot after 3 crests have had time to spread out. We could draw the rays, of course, and the rays show that this wave is moving out to the right. And then, again, we have the wavelength, which is the distance between 2 crests. So make sure these are all in your picture. Plane wavefronts is what we just drew. Those are what we just drew. Plane wavefronts. So each of these lines, up and down lines, each of these is a plane wavefront. They are produced by an extended disturbance, such as a long piece of wood dipped into the water. A plane wavefront could also be produced by a point disturbance. But you're probably thinking, wait a second, how is that possible? We just learned that point disturbances produce circular waves. Well, the funny thing is, after having traveled far enough, circular wavefronts can become so big and so spread out. They can become so spread out that they begin to approximate plane wavefronts. So this is no different from how the ground seems flat, even though it's actually curved. If there's enough separation from the source and the wavefront, the circular wavefront, even though there's some circle, even though there's some slight gentle arc to it, it will seem flat, just like the ground seems flat, even though there is some circle to it. So for plane wavefronts, those rays are parallel, and we saw that in the drawing, right? These plane wavefronts are all parallel to each other, like this bullet says. When a plane wave hits a barrier, it's reflected. When circular waves hit a barrier, they also are reflected. So turn to page 93 of your book and take a moment to look at the reflection of the circular wave. The reflected wave, it looks like it originates from some point beyond the other side of the barrier. And this is actually the exact same as the appearance of an image of yourself behind a mirror. When you look in a mirror, it seems as though you are standing somewhere behind the mirror and you're looking at this picture of yourself, or this, version of yourself positioned behind the mirror. The same is true for reflections of waves. They appear to originate from behind the other side of the barrier. And this is just this is generally true. Things that are reflected, like waves and images, appear to originate behind the reflecting surface. Plane waves are reflected by barriers, and a wave that travels towards the barrier has a special name. It's called an incident wave because it's coming toward the barrier. After it's reflected off, we call it the reflected wave. Angles that the rays make are always measured from a normal. So a normal is simply a line drawn at a right angle to the barrier. So here, let's see a drawing of this. Imagine we have this surface. This is a barrier, right? A reflecting surface. And here are some wave fronts, some plane wave fronts coming toward the surface. If a little more time passes, they'll bounce off the surface back toward this direction, right? So here's the ray, which shows the direction that these wavefronts are moving in. And then they're going to bounce off back in the other direction. And there's the reflected ray. So this is the incident ray, and the red is the reflected ray. Now when we draw these pictures, we don't draw all of these lines because that's a lot. Instead, we simply draw the incident ray and the reflected ray. So here I'm going to show you now the normal. It's a line perpendicular to the surface. And we use that normal to measure the angle of incidence. Right? So this is what this bullet says. And we use that normal to measure the angle of reflection. So we measure the amount of angle from the normal, not measuring up from the horizontal. So we measure from the normal line. Okay? That's what this bullet says. Here are some laws of reflection. This angle of incidence always equals the angle of reflection. And the incident and reflected rays are all in the same plane as this normal that we draw. So I want you to add in the labels that I've asked you to add on this picture here, this one at the left. Add the incident ray, label that. Label the reflected ray. Go ahead and label the barrier, the reflecting surface, or the barrier. And then also label one of these plane wavefronts. When a wave passes from one medium to another, part of the wave is reflected, and part of the wave is transmitted. So this is evident when you look at a window, right? Most of the light passes through a window, but some of it will reflect off to produce a faint reflection. That's why you can see yourself in a window. You can see the faint reflection of yourself in a window, but someone on the other side could still see you as well. Some of the light is being reflected back to you, and the rest is being passed through to them, so they see you. So the part that's passing through is called the transmitted wave. Transmitted wave. And this transmitted wave always has less energy than the incident wave because some of that incident wave is reflected, so not all the energy makes it through. When a wave travels from one medium to another, its velocity changes. So for example, if light is going down from air and it's passing into water, it slows down. There's a change in light's velocity when it goes from air to water. When a wave slows down during transmission, the wavelength decreases. Right? When the velocity decreases, so does the wavelength. If the wave speeds up, so does, if it increases, then the wavelength also increases. So whenever the velocity increases, the wavelength increases. So we're going to draw this. Imagine we have this surface, right? This is the surface of a flat lake, and I'm looking at it from the side, so this is going up toward the sky, and this is going down toward the bottom of the lake. And imagine we have these wave fronts coming in. They're plane wave fronts because they come from the sun, which is so far away that they all appear to be parallel to each other. So these are plane wave fronts. When these strike the water, they slow down. That's the first thing we've learned just now. Because they slow down, by the time this first one has moved a little farther, this next wavefront has caught up to it a little bit. So there's a moment when this wavefront is not moving as fast as this one, which is still in the air. The wavefront in the water moves slower, and the wavefront in the air catches up. So it gets a little closer to it. But then, of course, once they're in water, they all travel at the same speed, and they maintain the same separation. So they only are able to catch up to the preceding, each wavefront is able to catch up to the preceding wavefront only during that time when it's in water, when it's in the air, and the one in front of it is in the water. Right? And of course we could draw a ray. So finish this drawing off, complete this drawing. If a wave hits a boundary between two media at an angle, so this was head-on, no angle. If it hits at an angle, it refracts, which simply means it changes direction. So imagine, here's our incident ray, which is at an angle, right? And it has some initial velocity, and it's going to pass through this boundary. Maybe it's air on top and water down below. Well, we can measure the angle of incidence, and then if we measure the angle of refraction, we see that it's different from the angle of incidence. In other words, this wave, which has some incident velocity, doesn't continue traveling along the same line. It's deflected by some amount. And the difference between these angles shows us how much deflection there is. So the final velocity is going to be different, right? The refracted velocity is different.